December 16th, 1944, 5:27 a.m., Elsenborn Ridge, Belgium. The metallic taste of frozen condensation lingered on Obergefreiter Hans Kruger's lips as he adjusted the focus knobs on his Zeiss 8x25 binoculars, the optical lenses fogging slightly in the sub-zero temperature as he scanned the snow-covered ridgeline where American artillery positions had been dug into the frozen ground, with mechanical precision that spoke of industrial efficiency rather than battlefield improvisation. Through the pre-dawn darkness, Kruger could see the distinctive silhouettes of American 155mm howitzers positioned in carefully surveyed firing positions, their barrels elevated at mathematically precise angles that suggested fire control systems far more sophisticated than anything the Wehrmacht had encountered during 3 years of fighting across the Eastern Front, where Soviet artillery relied primarily on massed fires and overwhelming volume rather than precision targeting and advanced ammunition technology. The morning air carried the sharp, acrid smell of cordite residue from the preliminary bombardment that had begun Operation Herbstnebel. Hitler's desperate gamble to split the Allied forces in the Ardennes and recapture the vital port facilities at Antwerp through a surprise offensive that would demonstrate to the world that German military power remained capable of decisive strategic action, despite the industrial disadvantages that had plagued the Wehrmacht since the United States entered the war in December of 1941. But as Kruger studied the American positions through his binoculars, something about their defensive preparations suggested that the element of surprise had been compromised, that the Americans had been expecting this attack and had positioned their artillery units not for hasty defensive fires, but for carefully planned interdiction missions that would require unprecedented accuracy and coordination between forward observers, fire direction centers, and ammunition supply systems operating under combat conditions. The impossible claim had been circulating through German intelligence channels since early November of 1944, when captured American technical documents began describing artillery shells equipped with proximity fuses that could detonate automatically when they approached enemy personnel or equipment, eliminating the need for precise range calculations and impact timing that had governed artillery effectiveness since the invention of gunpowder weapons in the 14th century. According to these reports, which seemed so fantastical that most Wehrmacht officers dismissed them as obvious Allied propaganda designed to demoralize German troops before the winter offensive, American artillery shells contained miniaturized radar transmitters that could detect the presence of enemy targets and trigger explosive detonation at optimal distances for maximum anti-personnel effectiveness, creating airbursts that would devastate exposed infantry formations regardless of terrain features or defensive positions. The technical specifications described in the captured documents suggested that these proximity fuses incorporated electronic components so sophisticated that they bordered on science fiction, including vacuum tube circuits, radio frequency oscillators, battery power systems, and mechanical safety devices that could function reliably under the extreme acceleration forces generated when artillery shells were fired from rifled gun barrels at muzzle velocities exceeding 2,000 feet per second. Such technology seemed impossible to manufacture under wartime conditions, particularly given the complex precision engineering required to produce electronic components small enough to fit inside artillery shells while maintaining sufficient durability to survive the shock loads and rotational stresses imposed during high-velocity ballistic flight through atmospheric conditions that included temperature variations, humidity changes, and aerodynamic forces that would destroy conventional electronic equipment within seconds of leaving the gun barrel. Even more incredible was the suggestion that American factories were mass-producing these proximity fuses in quantities sufficient to equip entire artillery battalions for sustained combat operations, implying industrial capabilities that exceeded anything German engineers had believed possible, given the material constraints and manufacturing limitations that governed wartime production of precision electronic equipment across all combatant nations. The mathematical requirements for such production seemed to violate fundamental principles of wartime economics and resource allocation, particularly considering that each proximity fuse would require skilled technicians, specialized manufacturing equipment, rare metals, precision components, and quality control procedures that would consume industrial capacity desperately needed for more conventional weapon systems and military equipment. Amerikanische Fantasie, Kruger muttered to himself as he lowered his binoculars and checked his wristwatch, noting that the preliminary bombardment was scheduled to intensify at precisely 0530 hours, when German artillery units would begin the systematic destruction of American defensive positions that would clear the way for infantry and armor attacks designed to break through Allied lines and reach the Meuse River before American reinforcements could respond effectively to the surprise offensive. The frozen ground beneath his boots vibrated slightly as German 100mm howitzers began their firing sequence from concealed positions in the Eifel forests, their high explosive shells arcing through the morning darkness toward American positions that had been surveyed and targeted through weeks of careful reconnaissance and intelligence gathering by experienced artillery observers who understood the mathematical relationships between gun positions, target coordinates, and ballistic trajectories. But as the first German shells impacted among the American positions, Kruger noticed something unexpected about the response from the opposing artillery units, something that suggested capabilities far beyond conventional counter-battery fire and defensive bombardment techniques that had characterized artillery warfare since the beginning of the conflict. The mathematics of modern warfare were about to teach the Wehrmacht a lesson in industrial precision that no amount of tactical surprise or operational planning would be able to overcome. The impossible claim had first appeared in a captured American technical manual dated November 3, 1944, which described artillery ammunition equipped with variable time Bulge, VT fuses that could achieve burst accuracy within 3 meters of optimal detonation altitude, regardless of terrain features, weather conditions, or target movement, creating anti-personnel effectiveness rates that exceeded conventional time-fused ammunition by factors ranging from 3 to 1 up to 10 to 1, depending upon target density and protective cover availability, according to the manual, which had been recovered from a destroyed American ammunition depot near Aachen during the October fighting. Each VT fuse contained a complete radio transmitter and receiver system weighing only 1.7 pounds and measuring 5 inches in length, incorporating 147 individual electronic components including 4 vacuum tubes, 17 resistors, 23 capacitors, 8 inductors, 42 soldered connections, and a battery system capable of providing electrical power for up to 45 seconds of continuous operation under combat conditions. The technical specifications seemed to belong more in the realm of peacetime laboratory research than battlefield artillery ammunition, describing manufacturing tolerances measured in thousandths of an inch and quality control procedures that required individual testing of every electronic component before final assembly, along with environmental testing protocols that simulated the extreme acceleration forces, temperature variations, and electromagnetic interference conditions that artillery shells would encounter during high-velocity ballistic flight toward enemy positions. Even more incredible was the assertion that American production facilities were manufacturing these proximity fuses at rates exceeding 100,000 units per month, representing an output level that would require specialized factories, trained technicians, precision manufacturing equipment, and raw material supplies that seemed impossible to achieve given the competing demands for electronic components needed for radar systems, radio communication equipment, navigation instruments, and the countless other sophisticated devices that modern warfare required in ever-increasing quantities. The mathematical implications of such production numbers were staggering when calculated against known American artillery deployment patterns and ammunition consumption rates observed during recent combat operations across the Western Front, suggesting that the United States Army was planning to equip every artillery shell fired in the European theater with proximity fuses, transforming conventional artillery from an area weapon requiring precise range calculations into a precision instrument capable of achieving devastating effectiveness against any target within its blast radius. Unmöglich, laughed Oberst Friedrich von der Heide as he reviewed the captured technical documents in his command bunker near Monschau, the concrete walls around him vibrating slightly as American heavy bombers passed overhead at 25,000 feet. Their Pratt & Whitney R-2800 engines creating a deep, mechanical thrumming that had become the constant soundtrack of life in the German-held territory during the final months of 1944. Even the Americans cannot manufacture miracles. Von der Heide had commanded paratroop units since the invasion of Crete in May of 1941, had witnessed firsthand the devastating effectiveness of concentrated artillery fire during 3 years of combat across multiple theaters, and he understood better than most officers in the Wehrmacht exactly what it required to coordinate, supply, and maintain artillery units capable of sustained fire support operations under battlefield conditions that included enemy counter-battery fire, supply line interdiction, and the constant threat of air attack. The logistics alone seemed prohibitive for any military organization operating under wartime constraints, particularly considering that each proximity fuse would require individual transportation, storage, handling, and installation procedures that were far more complex than conventional ammunition types, while providing no obvious tactical advantages that could not be achieved through proven techniques involving careful range calculation, precise timing, and experienced forward observers who understood the mathematical relationships governing artillery effectiveness. Besides, added Major Wilhelm Piper, who served as von der Heite's intelligence officer and had spent considerable time analyzing captured American equipment and tactical documents. Look at the power requirements for these supposed electronic systems. Each fuse would need its own battery, its own radio transmitter, its own detection circuits. The weight alone would reduce the explosive payload by 20%. Whoa, yes, Piper spread several photocopied pages across von der Heide's desk, each one showing detailed technical diagrams of proximity fuse components that appeared to have been drawn by engineering draftsmen working with precision instruments rather than battlefield sketches prepared by combat intelligence personnel, suggesting either extraordinary attention to detail in American technical documentation or elaborate deception operations designed to convince German commanders that they faced technological capabilities far beyond actual American industrial achievements. And consider the cost, Piper continued, pointing to manufacturing specifications that described precision machining operations, specialized assembly procedures, and quality control testing that would require individual attention for every proximity fuse produced. Each one of these devices would cost more than a complete artillery shell using conventional fuses. The Americans may be wealthy, but they are not insane. The economic arguments seemed compelling when evaluated against known patterns of American military procurement and resource allocation, which had consistently emphasized mass production of proven weapon systems rather than experimental technologies that might offer marginal improvements in battlefield effectiveness, while consuming disproportionate amounts of industrial capacity and specialized materials needed for other critical military applications. The mathematics of wartime production favored simple, reliable solutions that could be manufactured quickly and efficiently using existing industrial infrastructure rather than sophisticated innovations that required new factories, specialized equipment, and extensive research and development programs that would divert resources from more pressing military requirements. At least, that had always been the conventional wisdom among military planners and defense contractors on both sides of the Atlantic. From the Krupp Works in Essen, to the Vickers factories in Sheffield, to the massive industrial complexes that had transformed American civilian manufacturing into the largest military production system in human history. The proximity fuse represented such a radical departure from this established approach that it seemed to violate fundamental principles of wartime economics and industrial organization that had governed military technology development since the beginning of the industrial age. The multiple independent sources began accumulating throughout the first weeks of December 1944, each one providing additional confirmation of American proximity fuse capabilities that seemed increasingly difficult to dismiss as propaganda or misinformation, despite their apparent contradiction of established principles governing wartime technology development and industrial resource allocation under combat conditions. Lieutenant Colonel James McPherson of the 2nd Armored Division had been captured during the fighting near Geilenkirchen on November 28th and interrogated at the Wehrmacht's primary intelligence facility in Bad Orb, where he provided detailed descriptions of American artillery operations that he had observed during 6 months of combat across northwestern Europe following the Normandy landings in June of 1944. According to McPherson's testimony, which was recorded verbatim by Hauptmann Ernst Hoffmann of the Wehrmacht Intelligence Service, American artillery battalions had been equipped with proximity-fused ammunition since early September and were achieving casualty rates against German infantry formations that exceeded traditional artillery effectiveness by factors of 4 to 1 or higher, depending upon terrain and target concentration. The shells burst about 20 feet above ground level, McPherson had explained during his 3rd day of interrogation, his voice carrying the matter-of-fact tone of a professional soldier discussing routine tactical procedures. Perfect height for maximum fragmentation pattern. Doesn't matter if your troops are in foxholes or behind cover, the airbursts get them anyway. McPherson's account was corroborated by intercepted radio communications from American artillery units operating along the Siegfried Line, many of whom used insufficiently encrypted communication channels that allowed German signal intelligence teams to monitor fire direction procedures and extract valuable information about ammunition types, firing techniques, and coordination methods that governed proximity fuse employment under battlefield conditions. On December 3rd, Private First Class Robert Kowalski of the 28th Infantry Division had been taken prisoner during a German raid near Hürtgen Forest and questioned extensively about American ammunition supply procedures, weapon maintenance protocols, and tactical doctrine regarding artillery support for infantry operations. Kowalski's statements, filed through normal prisoner of war processing channels and eventually forwarded to Wehrmacht artillery specialists, described logistical systems that seemed designed specifically to support widespread deployment of proximity-fused ammunition across all American artillery units in the European theater. "Every shell we fire has got one of those VT fuses," Kowalski had told his interrogators, using the American military designation for proximity fuses that had appeared in captured documents but had never been confirmed through prisoner testimony until his capture. "Supply trucks bring them up every night. Thousands of the things, all packed in special containers with foam padding and handling instructions." The consistency of prisoner accounts regarding proximity fuse employment suggested systematic deployment rather than limited experimental use, implying that American factories had indeed achieved the massive production rates described in captured technical documents and were supplying proximity fuses to artillery units across the entire Western Front, rather than restricting their use to specialized units or specific tactical situations. Swiss journalist Marcel Dubois, reporting for the Journal de Genève from his position as a neutral observer attached to international Red Cross operations in the Ardennes-Baumeulnies region, had filed several dispatches during early December that provided detailed descriptions of American artillery tactics and their devastating effectiveness against German defensive positions, including specific references to the unusual burst patterns and timing characteristics that distinguished proximity-fused ammunition from conventional artillery shells. "The American gunners appear to have solved the fundamental problem of artillery timing," Dubois reported in his December 8th dispatch. "Their shells detonate at precisely the optimal altitude for maximum anti-personnel effect, regardless of terrain features or range estimation errors that have traditionally limited artillery accuracy." Dubois's observations aligned closely with technical assessments prepared by Wehrmacht artillery officers who had studied the blast patterns and fragmentation effects observed at sites where American artillery had engaged German positions, revealing damage patterns that could only be achieved through airbursts timed with mathematical precision rather than the approximate timing methods that characterized conventional artillery employment. The captured diary of Captain Thomas Mitchell, an American artillery forward observer who had been killed during fighting near Vossenack on November 15th, contained detailed entries describing proximity fuse performance under various weather conditions, target types, and tactical situations, providing insights into American employment doctrine that emphasized the revolutionary capabilities of this new ammunition technology. "VT rounds are changing everything about how we fight," Mitchell had written in his entry dated November 10th. "No more bracketing shots, no more adjusting for range to breeze. Just call for fire and watch the target area get swept clean. It's like having precision instruments instead of hammers." As the technical assessments included in Mitchell's diary described proximity fuse effectiveness rates that seemed almost too good to be true, with single artillery batteries achieving target neutralization that would previously have required entire battalions firing conventional ammunition, suggesting that American artillery capabilities had increased by orders of magnitude rather than incremental improvements that might be expected from normal technological development. French resistance fighters operating in the Ardennes region had provided detailed reports to Allied intelligence services regarding German troop movements and defensive preparations, many of which included observations of Wehrmacht casualties caused by American artillery fire that exhibited the characteristic blast patterns associated with proximity fuse employment, creating casualty rates that seemed inconsistent with conventional artillery effectiveness even when fired by experienced gun crews using proven techniques. The mathematical precision required to achieve such consistent results suggested not only sophisticated fuse technology, but also fire control systems, range calculation methods, and coordination procedures that represented fundamental advances in artillery science rather than incremental improvements to existing weapons and tactics. The technical specifications of the American variable time proximity fuse represented a revolution in artillery technology that German engineers had neither anticipated nor understood, incorporating manufacturing techniques and electronic systems that transformed artillery shells from crude area weapons into precision instruments capable of achieving devastating effectiveness through mathematical certainties rather than the approximate timing methods that had governed indirect fire weapons since the invention of gunpowder. At the heart of this transformation was the Mark 53 proximity fuse, a miniaturized electronic system consisting of a radio frequency transmitter operating at 180 MHz with a power output of 25 milliwatts. A super heterodyne receiver tuned to detect Doppler frequency shifts in reflected radio signals, and a gas-filled Thybertron tube capable of triggering explosive detonation when the received signal indicated optimal target proximity, all contained within a cylindrical aluminum housing measuring 5.5 inches in length and 3.2 inches in diameter. While weighing only 1.7 pounds when fully assembled and tested, the transmitter section incorporated a miniaturized vacuum tube oscillator circuit powered by a thermal battery that generated 22.5 volts of direct current through an exothermic chemical reaction, initiated by the setback forces generated when the artillery shell was fired from the gun barrel, providing electrical power for up to 45 seconds of continuous operation while maintaining frequency stability within 0.1% across temperature ranges from minus 65 degrees Fahrenheit to plus 160 degrees Fahrenheit. The receiver circuit employed a crystal detector and amplifier system capable of processing radio signals with sensitivity levels measured in microvolts. Using frequency discrimination techniques that could distinguish between genuine target reflections and false signals caused by ground clutter, atmospheric interference, or electronic countermeasures, while maintaining detection reliability rates exceeding 95% under standard battlefield conditions including rain, snow, smoke, and electromagnetic interference from nearby radio transmitters. The mechanical safety system consisted of a centrifugal arming mechanism that prevented accidental detonation until the artillery shell achieved a rotational velocity of at least 14,000 revolutions per minute, plus a time delay circuit that disabled the proximity detection system for the first 4 seconds of flight to prevent premature triggering caused by radio reflections from the gun barrel, nearby terrain features, or other friendly artillery shells in flight simultaneously. The explosive train incorporated a lead-azide booster charge weighing 0.3 ounces that could reliably initiate the main high-explosive filling of the artillery shell when triggered by the Thybertron tube, creating blast effects and fragmentation patterns optimized for anti-personnel effectiveness at detonation altitudes between 15 and 30 feet above ground level, depending upon target density and terrain characteristics. Manufacturing each proximity fuse required 347 individual precision operations performed by skilled technicians using specialized equipment that maintained tolerances measured in thousandths of an inch, including vacuum tube assembly under controlled atmospheric conditions, crystal oscillator frequency calibration using precision test equipment, battery system quality testing under simulated combat acceleration loads, and final electronic performance verification using automated test procedures that simulated actual flight conditions. The production process consumed 23 different types of specialized materials, including silver-plated copper wire, precision ground quartz crystals, high-purity aluminum alloy, rare earth elements for vacuum tube filaments, specialized battery chemicals, waterproof sealants, and 47 categories of electronic components that were manufactured to military specifications, requiring reliability standards far exceeding civilian electronic equipment. Quality control procedures included individual testing of every proximity fuse using ballistic simulation equipment that subjected each unit to acceleration forces of 20,000 gravities for duration periods equivalent to actual artillery shell flight times, plus electromagnetic compatibility testing that verified proper operation in the presence of radio frequency interference from radar systems, communication equipment, and other electronic devices commonly found in battlefield environments. The final assembly process required clean room conditions with controlled temperature, humidity, and atmospheric pressure to prevent contamination of sensitive electronic components, plus specialized handling procedures that minimized static electricity discharge and mechanical shock that could damage delicate vacuum tubes or crystal oscillators during transportation from manufacturing facilities to ammunition storage depots and forward supply points. Environmental testing protocols simulated storage conditions ranging from tropical heat and humidity to Arctic cold and vibration levels equivalent to transportation by truck, railroad, and ship across intercontinental distances, ensuring that proximity fuses would function reliably after months of storage under adverse conditions, followed by immediate deployment to combat units operating under battlefield stress. The mathematical precision required to coordinate all these manufacturing processes, maintain quality standards, and deliver completed proximity fuses to artillery units in combat zones represented an industrial achievement that challenged fundamental assumptions about what was possible under wartime production conditions, transforming theoretical engineering concepts into mass-produced weapons through systematic application of American manufacturing expertise and resource allocation. It was the mathematics of industrial precision applied to the ancient art of artillery warfare, creating weapons that functioned with clockwork reliability while delivering devastating effectiveness that exceeded anything achieved through conventional ammunition technology. The central set piece began at 11:47 a.m. on December 17, 1944, when Obergefreiter Hans Kruger led his company of 276th Volksgrenadier Division Infantry across the snow-covered fields east of Elsenborn Ridge in a desperate attempt to break through American defensive positions that had been reinforced overnight with additional artillery units. Their 155mm howitzers positioned in carefully surveyed firing positions that commanded overlapping fields of fire across the entire approach route that German forces would be forced to traverse during their assault on the strategically vital high ground. Kruger's men advanced in extended formation across the frozen terrain, their white winter camouflage uniforms blending with the snow-covered landscape as they moved through the pre-dawn darkness toward American positions that seemed unusually quiet given the intensity of German artillery preparation that had been pounding the ridge since 05:30 hours, creating massive explosions and towering columns of smoke that suggested devastating damage to American defensive installations and personnel. The mathematical calculations seemed to favor the attacking force, as they had during countless similar operations across 3 years of combat on the Eastern Front, where German infantry units had perfected assault techniques that emphasized speed, surprise, and concentrated firepower applied at decisive points in enemy defensive lines that could be identified and exploited through careful reconnaissance and tactical analysis. But as Kruger's company approached within 800 meters of the American positions, something unprecedented happened that would fundamentally alter his understanding of modern artillery warfare and the industrial capabilities that American forces could bring to bear against German tactical formations operating under battlefield conditions. The American artillery response began with mathematical precision that seemed almost supernatural in its accuracy and timing, as a 155mm high explosive shells equipped with proximity fuses began detonating exactly 22 feet above the advancing German infantry at intervals of 1.3 seconds, creating a systematic pattern of airbursts that swept across the snow-covered fields like an enormous harvesting machine designed specifically for the destruction of human life. Each shell burst with devastating effectiveness that exceeded anything Kruger had experienced during 3 years of combat across multiple theaters, the proximity fuses triggering explosive detonation at precisely the optimal altitude for maximum anti-personnel effect, regardless of terrain features, defensive positions, or evasive maneuvers that had previously provided some protection against conventional artillery fire that relied upon impact fusing or time delay mechanisms. The mathematical relationship between burst height, fragmentation pattern, and casualty radius had been optimized through extensive testing and calculation, creating kill zones with diameters measuring 43 meters for each individual shell burst, while the systematic timing and placement of successive detonations eliminated gaps or safe areas that might have allowed German infantry to seek cover or continue their advance toward American defensive positions. Within 4 minutes and 17 seconds, Kruger's entire company had been effectively destroyed as a combat-effective unit, with casualties exceeding 78% among personnel who had been advancing across open terrain when the proximity-fused artillery barrage began. While the survivors found themselves pinned down in inadequate cover by continued artillery fire that seemed to anticipate their movements and adjust automatically to maintain devastating effectiveness regardless of tactical countermeasures. The precision of the American artillery fire suggested not only sophisticated fuse technology, but also fire control systems that could coordinate multiple gun batteries with mathematical accuracy, directing their fire through predetermined patterns that had been calculated to achieve maximum coverage of the target area while minimizing ammunition expenditure and battery exposure to German counter-battery fire. Kruger himself survived the initial barrage only because he had taken cover in a shell crater created by earlier German artillery fire. But as he attempted to organize the scattered remnants of his company for withdrawal to German lines, he discovered that American artillery units were maintaining continuous fire on the entire battlefield area using proximity-fused ammunition that made movement across open terrain essentially impossible for infantry forces lacking adequate armored protection. The systematic nature of the artillery response suggested advanced planning and preparation that went far beyond conventional defensive fire procedures, indicating that American artillery units had been positioned and supplied specifically to engage German infantry attacks using proximity fuses that transformed traditional artillery from an area weapon requiring precise timing into a precision instrument capable of achieving near-certain destruction of any target within its effective range. As the artillery barrage continued with mechanical regularity, Kruger understood that he was witnessing not merely superior firepower, but an entirely different approach to artillery warfare, one that emphasized mathematical certainty over tactical improvisation and industrial precision over individual marksmanship. Creating combat conditions where German infantry tactics developed through years of combat experience became irrelevant against weapons that functioned with the reliability and effectiveness of industrial machinery. The proximity fuses had transformed American artillery from a supporting weapon into a dominant battlefield system capable of controlling terrain through systematic application of devastating firepower that could not be countered through conventional tactical methods or defensive measures available to German forces operating under the material constraints and technological limitations that characterized Wehrmacht capabilities during the final months of 1944. It was not artillery fire as German soldiers understood the concept, but rather systematic destruction carried out with industrial efficiency that reduced infantry combat to a mathematical equation where superior technology and unlimited ammunition supply created tactical situations that could not be overcome through courage, training, or tactical skill alone. The systemic scale expansion of American proximity fuse production during the final months of 1944 revealed industrial mathematics so overwhelming that they transformed the strategic calculus of artillery warfare across the entire Western Front, creating logistical realities that German intelligence analysts continued to dismiss as statistical impossibilities, even as the evidence of American technological superiority accumulated on battlefields from the Siegfried Line to the Ardennes forests, where Wehrmacht units encountered devastating firepower that seemed to violate fundamental principles of wartime resource allocation and manufacturing capacity. The Johns Hopkins Applied Physics Laboratory had developed proximity fuse technology under a research program designated Section T, employing 1,047 scientists, engineers, and technicians working in specialized facilities that operated under the highest security classifications while consuming $23.7 million in research and development funding between 1940 and 1943, representing one of the largest concentrated scientific efforts in American history and producing innovations that challenged basic assumptions about what was possible in miniaturized electronic systems operating under extreme battlefield conditions. Manufacturing operations had been distributed across multiple production facilities to ensure continued output even under wartime disruptions, with primary assembly lines located at Eastman Kodak in Rochester, New York, Sylvania Electric in Salem, Massachusetts, Crossley Corporation in Cincinnati, Ohio, and Zenith Radio in Chicago, Illinois. Each facility employing between 2,300 and 4,800 specialized workers operating sophisticated production equipment that had been designed specifically for proximity fuse manufacturing under stringent quality control requirements. The Eastman Kodak facility alone was producing 127,000 proximity fuses per month by December of 1944, representing one complete fuse rolling off the assembly line every 19.7 seconds during round-the-clock production schedules that operated 24 hours per day, 7 days per week, consuming 847 tons of specialized materials including high-purity aluminum, precision electronic components, rare earth elements, and 156 different categories of chemicals and alloys that were manufactured to tolerances measured in parts per million. Raw material requirements included 23 to 400 vacuum tubes per month, manufactured to military specifications, requiring individual testing and quality certification. 89 to 700 precision resistors with tolerance ratings of plus or minus 1%. 156 to 200 capacitors rated for operation under acceleration forces exceeding 20,000 gravities, and two 30-40-600 soldered connections that were inspected using magnification equipment and X-ray analysis to ensure structural integrity under combat conditions. Battery production consumed 67,000 pounds of specialized chemicals per month, including lithium compounds, silver oxide, mercury, and thermal reactive materials that could generate electrical power through controlled exothermic reactions initiated by artillery firing forces. Each battery system requiring individual performance testing under simulated combat acceleration loads that reproduced the extreme conditions encountered during high-velocity ballistic flight. Quality control procedures required 347 individual inspection operations for each proximity fuse, including electronic performance testing using automated equipment that simulated actual combat conditions, mechanical stress testing that subjected components to vibration and acceleration forces equivalent to artillery firing, and environmental testing that verified proper operation across temperature ranges from -65 degrees Fahrenheit to +160 degrees Fahrenheit. Transportation logistics consumed 1,247 specialized railway cars per month, equipped with shock-absorbing suspension systems and climate control equipment to protect sensitive electronic components during transcontinental shipment from manufacturing facilities to ammunition depots and forward supply points. While ocean transport required 89 cargo vessels specifically modified with vibration-dampening cargo holds and electromagnetic shielding to prevent damage during Atlantic crossings under convoy conditions. Storage facilities at ammunition depots required climate-controlled warehouses totaling 2.3 million square feet of floor space equipped with specialized handling equipment, inventory control systems, and security measures appropriate for the most sensitive military technology. While forward supply operations consumed 156 specialized trucks equipped with shock-absorbing cargo systems and trained personnel capable of maintaining proper handling procedures under battlefield conditions. The electrical power required for proximity fuse manufacturing operations totaled 234 million kilowatt-hours per month, supplied through dedicated power lines and backup generators that ensured uninterrupted production even during peak industrial demand periods. While skilled labor requirements included 12,300 specialized technicians trained in electronic assembly, precision manufacturing, and quality control procedures that required 6 months of intensive education before workers could achieve acceptable production rates. By December of 1944, American factories were delivering completed proximity fuses to artillery units in Europe at rates exceeding 450,000 units per month, representing sufficient ammunition to equip every artillery shell fired by American forces with proximity fusing capability while maintaining strategic reserves that exceeded total German artillery ammunition production across all calibers and ammunition types during the same period. The total industrial effort represented by proximity fuse development and production consumed approximately 1.8% of America's total manufacturing capacity during 1944, including research facilities, production equipment, skilled workers, raw materials, transportation systems, and quality control infrastructure that operated with mathematical precision to transform theoretical scientific concepts into mass-produced weapons through systematic application of industrial engineering principles. It was an avalanche of numbers that represented the conversion of American scientific knowledge and industrial capacity into battlefield dominance through mathematical certainties rather than tactical innovation. The systematic transformation of advanced physics into practical weapons that could be manufactured in quantities sufficient to change the fundamental nature of artillery warfare. The enemy realization moment came on December 19, 1944, when Oberst Friedrich von der Heydt stood in his forward observation post near Monschau and watched American artillery units systematically destroy an entire regiment of German infantry with such devastating efficiency that the engagement resembled an industrial process rather than conventional artillery fire. Each proximity-fused shell detonating with mathematical precision that eliminated traditional concepts of cover, concealment, and tactical movement that had governed infantry warfare since the development of indirect fire weapons. Through his Zeiss periscope, von der Heydt observed the 12th Volksgrenadier Regiment advancing across snow-covered fields in perfect assault formation, their white winter camouflage uniforms creating disciplined lines that stretched across nearly 2 kilometers of open terrain as they moved toward American defensive positions that had remained silent throughout the German preliminary bombardment, suggesting either complete destruction of enemy artillery capabilities or tactical deception designed to lure German forces into a predetermined killing zone. When the American counter-battery fire began at precisely 13:47 hours, von der Heydt initially assumed he was witnessing conventional artillery response using standard high-explosive ammunition and time delay fusing that would require multiple rounds to achieve effective coverage of the target area, providing opportunities for German infantry to seek cover, adjust their approach routes, or continue their advance using tactical movement techniques that had proven effective against Allied artillery throughout 3 years of combat across multiple theaters. But what he observed instead was systematic annihilation carried out with industrial precision that defied everything he understood about artillery warfare and the mathematical limitations that governed indirect fire effectiveness under battlefield conditions. The American 155mm shells began detonating exactly 22 feet above the advancing German infantry at intervals of 1.7 seconds, creating a moving wall of steel fragments and explosive blast effects that swept across the battlefield with the mechanical regularity of factory machinery. Each airburst positioned with mathematical accuracy that eliminated gaps or safe areas where German soldiers might find protection from the devastating fragmentation patterns. Mein Gott, whispered von der Heide as he watched the systematic destruction of the 12th Regiment's 2nd Battalion. The proximity fuses triggering explosive detonation with such precise timing that individual shell bursts seemed coordinated by invisible calculating machines rather than human fire direction procedures. They are not firing artillery. They are operating machinery. Within 7 minutes and 43 seconds, the entire regiment had ceased to exist as a combat-effective unit, with casualties exceeding 89% among personnel who had been advancing across open terrain when the proximity-fused barrage commenced. While the few survivors found themselves scattered across a battlefield where continued American artillery fire made any form of organized movement or tactical coordination completely impossible, but it was what von der Heide observed next that truly revealed the scope of American industrial capacity and the mathematical inevitability of German defeat in any prolonged artillery engagement. As the American artillery batteries completed their fire mission and prepared to engage additional German targets, von der Heide noticed ammunition supply trucks moving forward to resupply the gun positions with what appeared to be unlimited quantities of proximity-fused shells. Each truck carrying standardized loads that suggested mass production and logistical systems designed to support sustained artillery operations at intensities that would exhaust German ammunition reserves within hours of comparable firing rates. The sight of dozens of supply vehicles delivering thousands of proximity fuses to American artillery positions struck von der Heide with the force of a physical revelation, not because of the immediate tactical implications, but because of what it represented about the fundamental mathematical relationship between American industrial capacity and German material limitations under total warfare conditions that increasingly favored nations capable of transforming entire civilian economies into military production systems. Each proximity fuse represented approximately 347 man-hours of skilled labor, 23 pounds of specialized materials, 156 precision components, and manufacturing processes that required facilities, equipment, and technical expertise that German industry could not hope to duplicate given current resource constraints and the constant disruption caused by Allied bombing campaigns against German industrial targets. The Americans were expending proximity fuses at rates that would consume Germany's entire annual production of precision electronic equipment within a single week of sustained artillery operations, treating advanced technology as expendable ammunition that could be replaced faster than it could be consumed, even under the most intensive combat conditions imaginable. "They have so much," von der Heide murmured, his voice barely audible above the continuing roar of American artillery fire that had shifted to engage additional German targets with the same devastating effectiveness. "So much that they use miracles like common ammunition." And for the first time since joining the Wehrmacht in 1933, von der Heide understood that Germany was not fighting an enemy army, but rather an entire industrial civilization that had transformed warfare into a manufacturing process, where victory would be determined not by tactical skill or strategic planning, but by the mathematical application of superior productive capacity against opponents who simply could not match the scale of American technological abundance and industrial efficiency. The realization struck him with the cold certainty of an engineering calculation. Germany could not win a war of technological attrition against an enemy that treated precision electronic equipment as expendable ammunition, and could produce proximity fuses faster than German forces could fire the shells that contained them. The mathematics were as clear and unforgiving as the laws of physics themselves, reduced to simple arithmetic that no amount of tactical brilliance or operational innovation could overcome. The closing thesis emerged with mathematical certainty during the final days of December 1944, as Wehrmacht after-action reports documented the systematic destruction of German infantry formations across the Ardennes, salient through the relentless application of American proximity fuse technology rather than superior tactics or individual marksmanship. transforming artillery warfare from a craft practiced by skilled gunners into an industrial process governed by production statistics and technological superiority, rather than traditional concepts of fire direction and ballistic calculation. By December 31st, 1944, the United States Army had expended 2,674,000 proximity-fused artillery shells during the Battle of the Bulge, representing more sophisticated electronic equipment deployed in a single military operation than Germany had been able to produce across all categories of precision instruments during the entire year of 1944. While American factories continued to manufacture proximity fuses at rates that would deliver an additional 1,847,000 units during the first quarter of 1945, creating technological superiority so overwhelming that German resistance became mathematically impossible rather than merely tactically difficult. The industrial mathematics that governed this transformation were brutally simple and absolutely decisive. American factories were producing proximity fuses faster than German artillery could fire the shells that would contain them. Even under the most optimistic assumptions about Wehrmacht ammunition supply and artillery deployment rates, while German industry remained incapable of developing comparable technology given current limitations in electronic component manufacturing, precision engineering, and the specialized materials required for miniaturized radar systems. Each proximity fuse expended during the Ardennes offensive was replaced by three new units arriving from American production lines within 8 days of its detonation. While each German artillery shell fired in response required raw materials that could not be replaced given current supply chain disruptions and manufacturing facilities operating under constant threat of Allied bombing campaigns that systematically targeted precision manufacturing capabilities. The German artillery arm, operating at maximum possible output under wartime conditions, could fire approximately 127,000 rounds of all calibers during a sustained artillery engagement lasting 7 days, while American artillery units consumed 847,000 proximity-fused shells during the same period, representing firepower superiority that exceeded German capabilities by a factor of 6.7 to 1 across all categories of indirect fire weapons. But the true measure of American industrial dominance lay not in total ammunition expenditure but in the systematic application of precision technology through standardized weapons systems that transformed individual artillery batteries into components of a larger industrial process designed to achieve fire superiority through mathematical certainty rather than tactical improvisation or individual crew training. The proximity fuses employed during the Battle of the Bulge achieved hit probabilities exceeding 94% against personnel targets in open terrain, compared to 23% effectiveness rates for conventional time-fused ammunition under similar conditions, creating casualty ratios that made German infantry tactics obsolete regardless of training, experience, or tactical leadership at company and battalion levels. This was not artillery warfare as German gunners understood the concept, but the industrial inevitability of superior technology systematically applied through production capabilities that German industry could neither match nor counter with existing resources under wartime conditions, that increasingly favored nations capable of transforming theoretical scientific research into mass-produced weapons operating with mathematical reliability. The mathematics of modern warfare had been permanently altered by American manufacturing methods that treated proximity fuses as expendable commodities rather than precision instruments. Artillery crews as trained operators of automated systems rather than skilled craftsmen practicing traditional techniques, and fire superiority as an engineering problem solvable through systematic application of superior technology and unlimited ammunition supply rather than tactical innovation or crew proficiency. German commanders had laughed at American proximity fuses because they understood artillery warfare as individual contests between opposing gun crews using proven techniques developed through years of combat experience. But the Americans had redefined indirect fire as an industrial process where victory belonged to the side capable of delivering the greatest amount of precisely timed firepower with the greatest degree of reliability over the longest possible period of sustained operations. As 1944 ended and 1945 began, Obergefreiter Hans Kruger lay in a field hospital near Bad Münstereifel and listened to the distant rumble of American artillery that continued day and night with mechanical regularity. Each shell burst creating the same distinctive crack of proximity-fused detonation that had first announced the arrival of weapons technology so advanced that it seemed to belong more in the realm of science fiction than battlefield reality. The metallic taste of frozen condensation still lingered on his lips as he remembered that December morning when he had first observed American artillery positions through his Zeiss binoculars, dismissing proximity fuses as impossible fantasies that violated fundamental principles of wartime manufacturing and electronic engineering under combat conditions. Now he understood that impossibility had been achieved through industrial mathematics so overwhelming that they transformed the theoretical concepts into practical weapons faster than German intelligence services could analyze and report their capabilities, creating technological realities that made traditional artillery warfare as obsolete as cavalry charges against machine gun positions. The proximity fuse represented not merely superior technology but the systematic application of American industrial capacity to the ancient problem of indirect fire accuracy, solving through mass production and precision manufacturing what German engineers had considered unsolvable given the material constraints and technological limitations that governed wartime weapon development. It was the mathematics of inevitability, expressed through proximity fuses that detonated with clockwork precision 22 feet above German positions. As reliable and unstoppable as the industrial civilization that had created them,